So let's continue our study of elasticity. In a previous lesson you saw this graph that shows the nature of the curve that compares stress to strain for materials that have some sort of elastic behavior. So if we go up to this point on the graph, we can say region number 1 represents the elastic range for the material, and anything beyond that point represents the plastic range. Now, all materials, if they're stressed too much, eventually reach some fracture point. And we're not going to study in much detail the plastic behavior of materials, and we're not even going to study this portion of the graph that says any additional stress produces an increase in the amount of strain, because this portion of the graph is nonlinear. So we're really only interested in a study of materials for which the relationship between stress and strain is linear. And so we're going to study materials within their proportional limit. So one example of a material within its proportional limit would be a ball that's submerged underwater. The result of submerging the ball underwater is an increase in fluid pressure that pushes in from all sides. So that's the stress involved. It's the additional pressure. The strain is some change in volume. So the ball starts out this large and ends up this large. Or maybe you have a piece of styrofoam in the shape of a cube. If you squeeze that styrofoam on all sides, something like a Nerf block or something like that, then the result is you get less volume in the end. So there's some initial amount of volume and some lesser amount of volume, and so the change in volume is the initial volume minus the final volume, and we could express our strain as a percentage. It's not just the change in volume, but it's the change in volume compared to the initial volume. How are we going to measure the stress? So the stress is just the change in pressure. So there's something known as absolute pressure. And the absolute pressure, well, right now there's some absolute pressure acting on your inner ear canal. That's mainly just due to atmospheric pressure. In other words, you're sitting at the bottom of the deep end of a pool right now. Now careful, figure not drawn to scale. I believe the radius of the Earth is about 4,000 miles, and I think the altitude of the upper atmosphere is about 200 miles. So you can see I'm not drawing my figure to scale at all, right? And certainly a person wouldn't be that large. But the weight of the atmosphere bearing down on you is an amount of pressure. All of the air in the atmosphere that lies above you has some weight, some value of mg, or maybe the integral of GdM or something like this, right? It's a non-uniform gravitational field, but in any case, all that air does weigh something, and that's a force pushing down. And then if we exaggerate this drawing and just imagine all the air above you lies in this cylinder that corresponds to the cross-sectional area that you occupy, then we can express atmospheric pressure as just a ratio of force per unit area. In any case, if you were then to dive underwater, all of the weight of the atmosphere would bear down on you, plus you'd have an additional amount of weight due to the fluid. And because water is so much more dense than air, 200 miles worth of air sitting above you has the same effect, I believe, as about 3 meters underwater. You can simulate one additional atmosphere of pressure by going about 10 feet in depth. So the absolute pressure acting on your inner ear canal when you go underwater is more than just the atmospheric pressure. it's also plus some additional pressure. So we might call this the gauge pressure. Because after all, when we try to measure the pressure of a basketball that's been inflated, well, if it's just starting to, what we say, go flat, then there's still some overall amount of pressure acting on. In fact, there's still 1 atmosphere of pressure. It's just not inflated beyond that 1 atmosphere. But I'm sure if we hooked up a bike pump to this that had a pressure gauge built into it, I don't think that's going to read the atmospheric pressure. I think it's going to read 0 in the case where it's going flat. So all of our gauges have been recalibrated, not to measure the absolute pressure on something, but to measure just the gauge pressure. In any case, pressure is a form of stress. And in the case of a cube, like Nerf material or sponge material that's been pushed on all sides, the stress is not the absolute pressure, it's just the increase in pressure beyond 1 atmosphere that causes it to have a deformation. And so the bulk modulus is expressed as the additional pressure compared to the fractional change or the percentage change in the volume.